Welcome to the next lecture in week 3 of the NPTEL Haskell course. In this lecture, we will be looking at a few other data structures that we have been using earlier but we have not introduced properly. We will look at characters, strings, tuples, etc. and a couple of very convenient data types that allow you to structure your programs better. Okay, let's look at the data type character. It's written CHAR with capital C. All data types in Haskell or at least all the built-in ones start with a capital letter. Your functions must start with a small lowercase letter. If you start something with an uppercase letter, most probably GHCI will complain. You should test it out. So in these slides, all the functions that I will write will start with a lowercase English letter. Okay, so now character values are written within single quotes, something like this: the letter A, the letter 3, the letter percentage, the letter hash, etc. And typically Haskell allows you to use any Unicode character, but for most examples we will just be using ASCII because we are trying to learn to program basic algorithms and not trying to create some library which processes international characters and so on. But just note that you can always use Unicode in Haskell if you want to, or ASCII. But the important thing is that character symbols are stored in a table, and there is an inherent table is just like an array. Think of an array. There is an order of elements. The table is like an array, so it will have indices 0, 1, 2, 3, 4, etc. There will be some character stored at index 0, some character stored at cell 1, etc., etc. So for instance, the character 0 will be stored right before the character 1, which will be stored right before the character 2, etc. as you would expect. The character A will be stored right before the character B. The character capital A will be stored right before the character capital B. But one does not immediately remember the order between small a and capital A or the order between 0 and small a. And nor do you need to remember these orders. Okay? Because you can always extract the corresponding order by these two functions, by this function called ORD. ORD is a function, let's for now think of it as having type char arrow int. CHR has type int arrow char. And they are inverses of each other. C is always equal to CHR of ORD of C, and J is equal to ORD of CHR of J, provided J is an index in the character table. I cannot try some really huge integer value and ask what is CHR of J. I might probably get an error. So important point is that ORD and CHR are not part of the standard library. Recall that I also said that the standard library is called Prelude, not part of the Prelude. But even inside GHCI, you can always say import data.char, and that will import a lot of functions and concepts related to data, related to characters. Okay, so here let us look at writing a function on characters. This is a simple function. It should convert lowercase letters to uppercase letter, but only if the letters are between small a to small z. If it is some so 2 upper is actually a built-in function, but we will in data.char, available in data.char. but we will try to see how you can program this. Okay, so 2 upper of small a will be capital A and so on. Otherwise it should stay the same. 2 upper of capital T, let us say, should just be capital T. 2 upper of the at symbol should just be the at symbol. Nothing else should change. 2 upper of 0, the 0 symbol should just be the 0 symbol. Here is one way to write this function. 2 upper of small a equals capital A, 2 upper of small b equals capital B, and so on and so forth. And just to complete the definition, you can say 2 upper of C equals C. C is a variable name, stands for character, not to be confused with the literal character C within quotes. C within quotes is a literal character C, whereas this C here is a variable name. Okay, I hope you understand this. You appreciate the distinction. So you can add that as another line, as an extra line. Now this will make the definition complete. If you give any lowercase letter, you will get the corresponding uppercase letter. If you give the any other input, it will stay, the output will just be the same as the input. And you could do that program, but that program is a very dumb program. It is a correct program though, this is exactly what you want. But what if you wanted to write something that changed 100 characters? You can't write 100 lines. Even this is too much. You have to write 27 lines of code for a very simple thing. Here is where you use the fact that A to Z have contiguous odd values. Okay, so you have some huge table. All kinds of characters are stored. But somewhere here, in contiguous locations, you store A to Z. And somewhere elsewhere, either later or before or wherever, in contiguous locations, you have capital A to capital Z stored. Somewhere else, I don't know, maybe here, the character 0 till the character 9 is stored, in all in one cell after the other, with nothing else coming in between. Yeah, once you start with small a, you will go small b, small c, small b, small c, etc., all the way till small z. Okay, similarly for capital letters, right? So now you can actually compare two characters to see which one appears earlier in the table, and that is just the less than or equal to. So this is the first time you will see that arithmetic operators, like relational operators, like less than, equal to, greater than, etc., these are all called relational operators. We know that less than or equal to, greater than or equal to, etc., is applicable on numbers. We know that equality check is applicable on numbers, but also on other values. So I can check whether C is the same as D, or F is not equal to Z, and so on. But what is interesting is that I can also check whether small a is less than or equal to small c, and what it means is that is A stored before C in the table of characters, that is what it means. Okay, so now since we know that A to Z are stored in contiguous locations, which means that between the letter small a and the letter small z, nothing else appears, only characters appear. So you can check whether, so here is an implementation of 2 upper. Check whether your input character C, your input is a variable named C. Once again, this is a variable named C, not the literal character. Okay, anyway, your input is C. Check whether A is less than or equal to C and C is less than or equal to Z, this means that C stands for a lower case. In which case, what you do is you have to find a new character, right? What is the new character? You have to offset. So from C, so you have a table. From your character C, you get its index. Go to index plus offset. That will be somewhere here, and find out what that character is. Okay. So, and we know that there are two functions. ORD gives you the index of a character. CHR gives you the character corresponding to an index. So, you do CHR of ORDC plus offset. Okay. This is what you do. What is offset? Offset is the order of capital A minus order of capital small a. Okay. So, somewhere you have small a till small z. Somewhere you have capital A till capital Z. You look at the index of this, some int1, and you look at this index, this is int0. Int1 minus int0 tells you how much you have to offset. So, if you have the character f, let us say, it is so many characters after, its index is so much after int0. So, you should find the character corresponding to the index which is the exact same offset after int1. Okay. So, this is essentially what this program is doing. Okay. You could do this. Of course, you needn't do all this. You can directly say 2 upper, and even these things, there are built-in functions for all this to check whether C is greater than or equal to small a and less than or equal to small z. You can use something called E is lower, E is upper. You can say is digit. The digits 0, 1, 2, 3 till 9 are stored in contiguous locations, and each digit will return that. You can say is alpha, which will tell you as if it is either lowercase or uppercase. You can also say is alpha num. These are all utility functions provided in data.char. Okay, and then you could do this, and also you have 2 upper, which is itself, which we have actually programmed. That is a utility function provided by Haskell, data.char. 2 lower, okay, etc. You have some very important thing that converts from a digit, which is a character. If it's just the single digit character, you can convert it to the corresponding number, and you can convert a number which consists of a single digit to the corresponding character. So, there are some functions for that as well. Yeah. So, as you can see, E space is white space, which means the space, but also some new line, tab, various things come under white space. Okay. Single space, which is usually denoted by a symbol like this. This denotes this symbol like an empty basket that denotes a single white space, a single space. Okay, this all comes under white space. Okay, we can do case conversion. You can do single digit characters. Digit to int will actually take something like this, and it will produce the number 0. Something like 8, and it will produce the number 8. Int to digit will take a single digit number, and it will produce the corresponding digit. Okay. So, these are useful utility functions for you to have. And you have numeric representation, ORD and CHR, like I told you. These are all provided in char. And now we have seen strings before, but now that we have also learnt lists, a string is just a sequence of characters. Internally, it is just a list of characters. So, string is a type synonym, as it is called, for character, okay, for list of characters. So, type synonyms are defined using the type keyword. Okay. We will later see that you can define your own data types, but for that you use the data keyword. Synonym just means it's just a word, another word which means the same thing, right? So it's a type synonym. So string is just another way to refer to list of characters. But you have a special syntax for strings. Rather than writing something like the list within square brackets, the character H followed by the character E followed by the character L, etc., etc., you can just put all those things inside one double quotes, inside a pair of double quotes. So the empty string, instead of denoting it by just the square brackets without anything in between, you can put double quotes without anything in between. So there should be no space or anything in between. If you put like this, then that would actually correspond to the list consisting of a single character, which is the space. But if you just do this, that corresponds to the empty list. So the very nice advantage of treating strings as lists of characters is that all the list functions that we have seen so far just work. So I can take length and I can ask length of, I don't know, Haskell. I'll get 7. I can take 3 of Haskell. I'll get Has. Yeah, all the list functions that you defined earlier, reverse, take, drop, etc., everything works for strings as well. Okay, so let's do some more programming with characters and strings. Let's say I want to search for a character in a string and I will call this occurs. So for instance, if I say occurs k in Haskell, I should get true. How would we do this? We will just do recursion on lists. Strings are just lists, right? So we could just do that. Occurs CS returns true exactly when C occurs in a string. So occurs, no matter what your character that you are searching for is, C here is a variable standing for character, S is a variable standing for a string. So its type is character or a string or a bool. So occurs anything of empty string is false. Occurs C in A colon S is either C equal to A, in which case you have to return true, or C occurs in AS. Okay, that's it. So this is the function. So for instance, if I say occurs occurs capital J in LeBron James, what will I have? I will have it will check whether J equals L, or but J equals L is false, and false or anything else is just the value of the next thing. So I'll implicitly, whenever the condition is false, whenever the comparison is false, I'll implicitly just go on to the recursive call. So occurs J LeBron James is occurs J in LeBron James equals occurs J in LeBron James, etc., all the way till occurs J in James. But that will reduce to J equals J or something else, but this itself is true, so you will get the value true. Okay, so this is how this happens. It's just a standard list function. In fact, this is just a very particular case of a function called elim, which for now you can think of as A arrow list A arrow bool. But of course, it doesn't work for all lists. It works only for lists whose base type allow equality checks. Okay, so that you will represent by writing elim is a function from a arrow list a arrow bool of type a arrow list a arrow bool, provided a belongs to the equality class. Okay, we will talk about type classes later in a couple of lectures, don't worry about it. So just to tell you that this occurs is just a very specific instance of the elim function. Elim checks whether a character is, whether a value is an element of a list. Okay, so that is occurs. Here is capitalize, it's a function. What it does is it goes through every letter in a string and turns it into capital, its capital letter form. It's simple. Capitalize of empty string is empty string. Capitalize of a colon a is 2 upper a followed by capitalize of a's, right? So it's a simple recursion, but it's a nice pattern to remember. You will see that this kind of pattern might occur quite often. I might say, for instance, remember long ago we in the previous lecture we had an add one. Add one of empty list is empty list. Add one of x colon x's is x plus 1 followed by add 1 x's. Essentially, you are applying the same transformation to every element in a list, and this is one pattern which can be generalized into a, we will see what Haskell will do this. It will generalize this to something called map, which we will look at in some 3 or 4 lectures. Okay, so we looked at occurs. Occurs returns a Boolean value depending on whether C occurs in S or not. But now we can consider this function position, which will return the index of the first position in S where C occurs. But C need not occur in S also. In that case, we will actually return the length of S. Okay, you will return the length of S if there is no occurrence of C in S. Okay, so how would we do this? We would say position anything in empty string is 0, and this is fine because empty string does not contain any occurrence of any C or anything else, and the length of empty string is 0. Okay, so we have done this. Position of n C colon C's, if n is less than or equal to 0, sorry, position of C in A colon A's. If C is the same as A, then 0, else position of C in A's. Right, that is a very simple recursion. So, for instance, position of A in battle axe should be 1. That is the first position of S in C occurs. Even though there are 2 occurrences of A here and here, we just want to return the index of the first place where A occurs. Position of D in battle axe is 10 because the length of battle axe is 10 actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, indices are from 0 to 9, right? This is index 0 and that is index 9. This is index 6. Okay. So, so when you say 10, since there is no index 10 in the string battle axe, you know that D does not occur in that string. Here is a simple recursive program. Position of C in any in the empty string is 0. Position of C in D colon D is, if C is equal to D, you return 0. Otherwise, you say 1 plus position of C in D. Okay. Here is another more challenging program, more challenging example. You want to count the number of words in a string. Okay. But first we need to figure out what a word in a string is. Okay. Words are separated by white space clearly, but there can be more than one white space. This is the point. So, I can have Haskell is cool. Okay, there is so many, let us say there are like some 15 there are some 4 tabs there and some 15 spaces here, let's say. Still you should count this as having 3 words, okay. So this string has 3 words. So you cannot count the number of words in a string by counting the number of spaces in the string and adding one. That won't work, okay. This is just to tell you that, okay. So yeah, so maybe you can count the number of white spaces in the string. You're saying word C of empty string is 0, word C of D colon D, word count in D colon D is, if D is a space, then 1 plus word count of D is, otherwise you just give word count of D's, let us say. Yeah, this won't work because word count of A, B, C, D will return 5, there are only 2 words there, okay. And there are other mistakes also that might happen in this, other errors also in this program, okay. We leave it to the reader to figure out what are all the kinds of errors that this program has. Yeah, so to determine when a word starts when the previous character is a white space and the current one is not a white space. That is the definition of a word. That is the definition of a start of a word. This is more or less true except for the first word in a string, because your first word in a string is just a character, could just be a character. We will come to that in a minute. But in general, you will say that a word starts when the previous character is a space and the current one is not. And all you want to do is you want to check the number of times such a pattern occurs. And since the very first word might start without your string itself could start with just a character, and therefore this logic will fail. What you do is word C, word count of S is actually go of space followed by S, okay. You add a space character by fiat and then you just run this go program, which is a local program. In this case I have just made it global, that's fine. It's an auxiliary program, okay, it's an auxiliary function. What it does is to count the number of space to space to non-space transitions, that's all it does. But by artificially adding a space at the very beginning, we are also counting the first word as a word, okay. So go of a single character is 0. It's a single character string here, and that should be 0 because you only have a single character, and therefore there is no space character to non-space character transition, okay. So notice here also that we are using a different pattern of pattern matching recursion. You would usually say go empty list and then go C followed by C's, but here we are saying we are not going to apply go on the empty list at all, because at the very first time when we call go, we are actually calling it on the string is preceded by the space character. So our base case now becomes the singleton list, and our recursive case should now therefore at least have 2 elements, C followed by D followed by D's, okay, that is our recursive case. So that's what you will see in the pattern matching here. Go of singleton list containing C is 0, go of C followed by D is if there is a transition between space to non-space in this, so which I will check by saying E space C and not E space D. That happens, then I will say 1 plus go D colon D's, otherwise I will just say go D colon D's, okay. So I am just counting the number of transitions between space to non-space, okay. This is a very clean and reasonably simple and reasonably elegant but very correct word count, okay. Okay, so we have seen characters, we have seen strings, we have seen some programs involving these. We have already seen many examples involving tuples. We had split add, for instance, and we had many other examples. Even in reversing an integer, we did somewhere we had to do div mod, and that returns a pair, okay. And I also mentioned that if I have a pair AB, then first of AB gives me A, second of AB gives me B. But it is not just pairs that I can have triples, quadruples and so on, and the syntax is simple. And the nice thing about tuples is that in lists, all the elements have to be of the same type. In tuples, the elements could be of different type, and in fact, most often it is of different types, because a tuple is just a way of putting together multiple pieces of information about some entity. Okay, here is for instance student element, the name is Suresh, some ID is this, and some date of birth is this. Okay, this is some fictitious Suresh because clearly my date of birth is not Jan 1 2000. Okay, good. So this is it. So this is of type string comma, it's a triple, it's of type string comma int comma string. In other languages, instead of using tuples, you might use struct, or in Java and so on class, but typically you will use structs in C and in Swift and other languages. This will store various pieces of information related to some particular entity. In general, it is also called records, comes from database terminology, because this is really a student record. Each line of corresponding to a student, you are storing various information, right? So this is also called record, and that at the very primitive level you can represent that using tuples in Haskell. And tuples are very simple, very convenient, because you can have functions that return tuples like div mod, etc. And that's very useful to return two pieces of information together. Here is lists of marks in a course, and this is very nice because this is also something that you might think of as a map. Okay, because it is taking this list itself is of type list of pairs, where each pair is of type string comma int. The string is the name and the int is marks, let us say, right? And this is like a map. The string is the kind of a key, and you look at the key and the value is the marks. Okay, and yeah, you can write various functions on this. So here is a pair of integers 3 comma minus 21. Here is a triple 13 comma true comma 97, which is of type int comma bool comma int. Here is a pair where the first element is a list of integers, second element is a string, and so on and so forth. You can have various such different kinds of tuples. Now the first and second functions are available for pairs. They are not available for other tuples of other lengths, but you can always use pattern matching. Okay, so yeah. Okay, so now I mentioned that this list here is kind of a map. I said this is also a map. You can view it as a map where the key is string and the values are integers. Now in a map, if I am given a map, what can I do? Given a key, I can search whether what is the correct value corresponding to the key. Okay, and that is usually called lookup, map or table as it's called, or you can even call it table. Lookup, I can ask lookup string arrow list of string comma int pairs should give me an int. Okay, so now what is the functionality I want? If this string is present in that list, I should return the value corresponding to the first occurrence of the string in the table. Okay, so one particular program I can write might be lookup of key right. KV is key values. the first key value is some k prime comma v, and I am looking up the key k. If k equals k prime, I will return the corresponding value. Otherwise, I will look up k in kvs. But what I have not specified in this program is what will I do if I do lookup of k empty list, right? I need to be able to give a sensible value. Now, in the case of list of marks, I could say that if a name is not even present, then I will return 0 as the marks, okay? But that's clearly ad hoc. Maybe I need to specifically say that whoever is doing the query on this table, I need to tell them that this name is not even present. Maybe some student was absent for the exam, and you need to be able to tell the instructor that the student was absent rather than just returning 0, because you can also score 0 in a test, right? So you shouldn't be returning, you shouldn't return default values that could also be possible legitimate values. Maybe you will say that if in the case of marks, maybe I will return negative marks, minus 100, but who knows, your test might involve negative marking, okay? So it is always ad hoc if we have to write a solution like this. So which leads us to the next topic, which is called maybe, okay? Here, okay, for that we will go back to a simpler example, which is that of position. Position of the character C in a string S. What we said was, if C is not in S, return length of S. This is okay in some situations, but it is not okay in certain situations. Sometimes you really want to be able to tell that a more direct way to tell that the character is not present in the string, okay? Rather than if somebody calls position, if I make a call to position of some x in some long string, and then I return some 100, let's say, then I need to do various things, right? I need to compare whether 100 is actually the length of the string, right? If so, then I have to say that, oh, therefore this x is not present in the string. I need to do some extra work. So after calling position with whatever x and whatever string it is, remember that I won't be giving a literal string here. I will typically, that string will be the value returned by some other function, right? Position of x in some other f applied on some mn, okay? That f applied on mn returns a string. I am asking if the character x is present in that string, and now, I mean, if I return the value, if I get back the value 100, I need to then check whether, check if length of lots of extra work just to determine that x was not in that string at all, okay? So yeah, position of C S equals length S indicates that C does not occur in S. So typically you will have some exceptional cases like this in code, quite often when you write code, and it is not advisable to return some normal values in those cases, and then force the caller of the function to make some checks like position C is equals length S, etc., etc. You need a more direct way to indicate non-occurrence, and that is done by using the maybe int type. Okay, so maybe int is really, if you want to think about it, it is integers along with a null value. Right, so the character might not occur in the string at all, in which case I have to return a null value, but it might occur, in which case I will have to return an integer. But the normal way of programming, so I mean, so then you need to do various null value checks at the site where you call the function, rather than checking for length s, etc. Haskell offers a neat way of doing this. It's called maybe int. So we'll look at this. Not just maybe int, I can have maybe char, maybe bool, maybe list of char, list of double, let's say. In fact, I can have maybe a, no matter what type a is, okay? For all types a, there is a maybe a type, okay? So maybe I'll drop some jargon right now. Maybe is what is called a type constructor, because given a type, it constructs a new type. Maybe is a way in which you can produce a new type from an existing type. Okay. We have already seen some other type constructors, though not by name. The parentheses which we use to construct tuples are also type constructors. Given some 4 types, I can construct a type of values where the first component is of this type, second component is of this type, third component is of this type, and fourth component is of that type. And the square bracket you can think of as a type constructor constructing lists. Given any type, I can construct a list of elements of that type. So, yes, so that's also a type constructor. We will talk about this in more detail few lectures down the line. But maybe it's quite important that I wanted to introduce it right now. And there are always 2 kinds of values for maybe t. One is a null value, which Haskell calls nothing with a capital N. Another is a normal value, but normal values are always tagged. You don't have untagged values, right? Because x can only be of type integer. X cannot be of type maybe integer. This is right, this is wrong. Okay. So, to make it to be of type maybe integer, you would put a tag, and the tag is called just. Okay. Just 5 is an integer. Okay. So, now what one can do now is, therefore, in this position I can change the signature of the function to char arrow string arrow maybe int. Okay. And position of C in empty string is nothing. Okay. This is a null value because C does not occur in the string. So, there is no position at all. Position of C in D colon D is if C is equal to D, then I return just 0. Otherwise, I will have to make a recursive call to position C and add 1 to it, but position C is not returning a simple integer, it is returning a maybe integer. So, I will get something called just 5 and I want to add 1 to it. I can't just add it. Here is where case construct is used. We will see that there is a clean way of doing this later, much later though. But for now, what you can do is you can use the case construct. Position C D is you make the recursive call, then you do a case analysis of the return value. In case it is nothing, you return nothing. In case it is just x, you return just x plus 1. Okay. So now position of something like position of k in Haskell will be just 3, right, because it is 0, 1, 2, 3. Position of k in Suresh will be not 6, but it will be nothing. Right? Okay. And okay, so just like maybe is now adding a null value to a existing type, right? So, you have integers, etc., etc. You have a new type where each integer is given a tag called just, and there is a null value called nothing. There is another kind of modification you can make to a type, and that is called either. And here is a simple usage. So, either looks like this, either A, B. Okay, it can have values of 2 kinds, left A or right B. In other languages, this is called the sum type or union type. In something like C, this is called okay. In Haskell, these are Haskell also. So, Haskell calls this is the either type constructor. This is a type constructor that takes 2 types and returns a new type, and the value at position, the function that we introduced earlier, we had an error. We use the error function here. The error function prints a nice error message, but what it also does is it immediately aborts and there is a runtime error. So, instead what you could do is you could use the either string integer type, and values of type either A, B is you have one kind of value, one set of values of the form left x where x belongs to type A, another set of values of the form right y where y belongs to B. Now you can actually do this. Value at position n, if n is less than 0, you can give left negative index. You can give one type of error message. But error messages are all from the left side, okay, left negative index. Value at position, anything of empty list is where you say left index too large, meaning left is just saying that it is the left part of the either type, okay. Okay, if for the normal values the integer values are right, so because they belong to the right argument of the either type constructor. So value at position 0 x colon x is right x, value at position n of x colon x is value at position n minus 1 of x is. This is just standard. So this maybe and either are some useful things that you could that is good to know. So I am introducing it right now. And once again, if you just like with the maybe type, you have to do case analysis. So some other function calls this value at position. So case value at position NL of, if it is left and then you get an error message, you handle it appropriately. If it is right and you get a value n, you handle it appropriately. Okay. So this is also related to what is called exceptions, and this is a way of doing exception handling in Haskell, sort of manually. Okay. This is enough for now. We'll perhaps we won't see in this course exception handling at all, but we will learn enough so that you can actually understand exceptions, etc., how it behave in advanced Haskell. Okay. I shall stop this lecture now. In the next lecture, we will have a demo session where we will look at some built-in list functions and maybe some of these functions that we have learned using maybe and either and so on. So thank you for now.